In this video I will be explaining some matrix operations. The first operation of matrices is what we call scalar multiplication. Assume that we have a matrix, let's see a matrix, and here are the elements of the matrix. If k is any real number, then the scalar multiplication of a by k is given by, so this k will be a number, but remember, a number is also a matrix. But in this case, the number will be considered just a scalar. So remove the bracket and you think of this as a number. So the scalar multiplication, k multiplied by a, so this k is a number, this a will be a matrix. You can type it in this way, or you can type it in an opposite way, a multiplied by k. That will be equal to the same matrix multiplying every entries of the matrix by the number k. So if you multiply a scalar, a number, by a matrix, multiply every entries of the matrix by this scalar. So the answer will be another matrix. So when you multiply this k by the matrix, the answer will be another matrix. And the entries of the new matrix will be the entries of the original matrix multiplied by k. So what you need to do is multiply every entries of the matrix by the scalar k. So the entries of matrix Ka are the entries of A multiplied by K. For example, -3, this scalar multiplied by this matrix. What you need to do is multiply -3 times 2, -3 times 4, -3 times -5. So multiply each element of the matrix by this -3, and the answer will be also a matrix. So this will be the answer, -3 times 2. -3 times 4. So you have multiplied every entries of the matrix by this -3. If you do that, here will be -6, this will be -12, this will be +15, this will be -6, this is -3, and this is 0. So you can type the matrix. The answer will be always a matrix of the same size. Another example, if B equal this 3 by 3 matrix, compute 1/2 of B. We can say 1/2 of B, or you can say 1/2 multiplied by B, or 1/2 times the B. If you made this multiplication, what you need to do is multiply 1/2 by every entries of the matrix. So 1/2 of B will be 1/2 of 2, 1/2 of 4, 1/2 of 1, etc. So this will be 1/2 of 2 is 1. So you cancel and the answer is 1. Here will be 4 divided by 2 is 2. So this entry will be 2. This entry will be 1/2 or 0.5 if you are using decimals. This entry will be 5/2. This entry will be -6/2. That is -3, etc. So that will be the answer. Every entries of the matrix multiplied by 1/2. So this is the first matrix operation. The second matrix operation will be the matrix addition. So you need to have two matrices in this case. The two matrices need to be of the same size. If matrix A is this matrix, matrix B, if you are going to add A plus B, will be something similar, B11, B12, B, etc. until B1 ends. Because if this matrix have m rows and n columns, then the matrix B need to have the same size, m rows and n columns. And adding the two matrices actually is adding one by one the components of the matrix. So the answer will be another matrix, so A plus B. So this is the addition of the two matrices, and it will be another matrix of the same size of the original matrices, in which every entry will be the sum of the corresponding entry of the matrix A and B. So that will be the answer for sure. So the first component of the first row, first column of matrix A plus B will be the element in the first row, first column of matrix A plus the element that is in the first row, first column of matrix B, etc. So what you need to do is add together the corresponding elements of the matrices. So matrix addition is defined only in matrices of equal size. So the only way that you can add two matrices is they have the same size. The entries of matrix A plus B is the sum of the corresponding entries of A and B. For example, if you have this 2 by 3 matrix A, matrix B need to be 2 by 3 also. So, and B equal this. Then A plus B will be 2 plus minus 3, 2 plus 2, negative 3 plus 0, and again 5 plus A, etc. So always for each entry you need to add the two corresponding entries of the original matrix, and the answer will be a matrix of the same size of the original. So again, this matrix will be a 2 by 3 matrix. So this number 2 plus minus 3 is negative 1, this is 4, this is negative 3, this is 13, this is 9, and this is 8. So the answer will be this matrix. The next operation will be, of course, matrix subtraction. If A is this matrix and B is a matrix of the same size, the subtraction is defined in a similar way that the addition. So you subtract the corresponding element of the first matrix with the corresponding element of the second matrix. So the answer will be a matrix of the same size. If you are subtracting two matrices, then the first element in the first row of the answer will be A sub 1 1 minus B sub 1 1. So the elements in the first row, first column of matrix A minus the element in the first row, first column of matrix B. And do the same with each element. So the entries in matrix A minus B will be the entries of matrix A minus the corresponding entry of matrix B. And again, the answer will be a matrix of the same size. So matrix subtraction as addition is defined only in matrices of equal size. And entries of the matrix A minus B is the difference of the corresponding entries of A and B. For example, if we have these two matrices, the same matrix that we had before, A and this is B, they have the same size. So A minus B will be 2 minus minus 3, 2 minus 2, minus 3 minus 0, 5 minus 8, 0 minus 9, etc. Do this operation, 2 minus minus 3, this is the same of 2 plus 3, this is 5, this is 0, this is negative 3, this is negative 3, 5 minus 8, 0 minus 9 will be negative 9, 4 minus 4 equals 0. So this will be the answer for this. So these three operations, scalar multiplication, addition, and matrix subtractions, are very easy, and the answers are always matrices of the same size. The next operation will be matrix multiplication. But before knowing what is matrix multiplication, let's learn how to make this type of multiplication. First, we're going to have a row vector and then a column vector, or better, a row matrix by a column matrix. So the multiplication will be defined so far with the first matrix, a row vector, and the second matrix, a column vector. We are going to see later what is the reason that the multiplication is defined in the way I'm going to tell you. For example, if we have a row vector like this, have n components, R1, R2, Rn. This is a row matrix or a row vector. And we have a column vector of the same size. Let's call it C1, C2, Cn. A row vector by a column vector will be just multiplying the first element by the corresponding element of the column. It will be R1 times C1, R2 times C2, etc. until Rn times Cn. So you multiply the corresponding element. So this product Rc is obtained by multiplying the corresponding elements and adding together these products. So there is not only a multiplication. Rc will be R1 times C1 plus R2 times C2 plus, I will be using this symbol for adding when I say adding together all the elements. So the sum of all the elements are ICI. So it will be equal to R1 times C1 plus R2 times C2 plus R3 times C3, etc. until the last element that will be Rn times Cn. adding together, obviously, it will be a number. So the result is a number. So this multiplication between vector is defined with some conditions. The vector must be of equal size, so they cannot be different size first. The first one in the multiplication must be a row, and the second one is a column. So far we have defined multiplication when the first element is a row and the second matrix is a column. So for example, this 2 minus 3 multiplied by negative 3a3. Of course, here a times b is defined. You will multiply 2 times negative 3 plus 2 times a plus negative 3 times 3. So then ab will be 2 times negative 3, 2 times a plus negative 3 times 3, negative 6 plus 16 minus 9. And this is 16 minus 15 equal 1. Okay, so we have a row vector 1, negative 2, negative 3, 0.5. And we have here another vector that is a column vector, let's call it D. There's negative 0.3, 2, 0, and 1.2. If you want to multiply C times D, obviously it's defined. This will be 1 times 0.03, that it will be negative 0.3. Negative 2 times 2, that will be negative 4, yeah? So it will be minus 4. Then negative 3 times 0, that is 0. And then 0.5 times 1.2, that is 0.6. So it will be plus 0.6. Add together all these numbers, 0.6 minus 4 minus 0.3. The answer that I get is negative 3.7. Okay, good. So that is the operation between a row vector and a column vector. This will be useful to define multiplication of matrices. For defining this multiplication of matrices, we are going to take into account that any matrix can be considered as the arrangement of row vectors. So if we have a matrix like this, you can see that this is a row vector. This is a matrix of size m by p. Do you notice? Because they have p columns and m rows. This matrix can be considered as this matrix. It's like a matrix of rows. We have 1, 2, and m rows. And obviously, if that is the case, we can type it in this way: R1, R2, Rm. So this matrix is actually equivalent to this matrix. The first element is a row, the second element is a row, the last element is a row. Again, the matrix also can be considered as an arrangement of columns. For example, if we have a matrix B like this, so we can think that this matrix is like this arrangement of columns. And then we can type it in this way: C1, C2, Cn. When we are multiplying two matrices, we are going to consider the first one as an arrangement of rows and the second one as an arrangement of columns. So we use this feature of matrices for defining the matrix multiplication. So let A be an arrangement of rows. And this, of course, will be of size m by p. So it will be a matrix that are like this. Yeah? We have p columns. I don't know how much is p. Could be 3, could be 20. And b is going to be considered an arrangement of columns. The second matrix will be considered as an arrangement of columns. So it will be a matrix of size p by n. This will be important. Look at this is p, the number of columns of the first matrix need to be equal to the number of rows of the second matrix. Then the product, let's call it M, AB, will be a matrix of size m by n. Oh, this is important so far. We need to have that the number of columns of the first matrix need to be the number of rows of the second matrix. But also we know now that the answer will be a matrix of size, the number of rows of the first matrix by the number of columns of the second matrix. Such as each element of this matrix, this is the element that is in the row I and column J of M, the matrix result, will be given by the multiplication of the row I of the first matrix multiplied by the column J of the second matrix. So the elements that is located in row I and column J of the matrix multiplication, we call it the matrix product, will be the multiplication or the product of the row I of the first matrix multiplied by the column J of the second matrix. For example, if we want to compute what will be the elements in the first row, first column of the product, it will be the multiplication of the first row of the first matrix multiplied by the first column of the second matrix. So these two numbers actually indicate which row and which column you are going to multiply. So let's see what we have so far. For the matrix multiplication to be defined, the number of columns of the first matrix must be the same as the number of rows in the second matrix. Second, the size of the matrix product is the number of rows in the first matrix by the number of columns in the second matrix. So the first thing is telling me when I can make a multiplication, but the second is telling me what will be the size of the product. And C, the entry located in the row I and column J of the matrix AB must be the product of the row I of the matrix A and the column J of the matrix B. Let's see an example. So assuming that we have this matrix 2, 4, -5, 2, -1, 0, and this is matrix A, the first matrix, and the second matrix is 2, 1, 0, 3, and we want to multiply A times B. So we notice here that A is a 3 by 2 matrix, 3 rows, 2 columns, and B is a 2 by 2 matrix. And we observe that the number of columns of the first matrix is the same of the number of rows of the second matrix. So these two numbers here in the middle need to be the same to be the multiplication to be defined. This is what this item A is telling me. And also the item B is telling me that the size of the answer will be a 3 by 2 matrix. So these two numbers at the end tell me what will be the size of the product. So I know that the answer will be a 3 by 2 matrix. Okay, so to find, for example, in the product, what will be the elements in the first row, first column? We multiply row 1 of the first matrix by column 1 of the second matrix. So M11 will be 2, 4 multiplied by 2, 0, multiplied by this column 2, 0. And this will be 2 times 2 is 4, and 4 times 0 is 0, so it will be 4 plus 0, it will be 4. Okay, so I know what will be the element M11. I want to know what will be the elements in the first row, second column of the product. We multiply row first of A by column 2 of B. So we multiply this 2, 4 by this 1, 3. So M12 will be the first row of the first matrix multiplied by this second row 1, 3. So it will be 2 times 1 plus 4 times 3. And this is 2 plus 12 equals 14. So this element in the first row, second column of the product will be 14. And what about M21? It will be the second row of the first matrix multiplied by the first column of the second matrix. So it will be -5, 2 multiplied by 2, 0. So it will be -5 times 2, that is -10, and 2 plus 0, that is 0 plus 0. So it will be -10, the answer. M22, so it will be second row, second column, second row, first matrix, second column of the second matrix. So it will be -5, 2 multiplied by 1, 3. So it will be -5 plus 6. So it will be 1. Yeah. We can find M31. So it will be third row, the first column. So it will be 1, 0 multiplied by 2, 0. This will be 1 times 2 is 2 plus 0 is 2. So it will be 2. M32. M32, so it will be the third row, second column. And we know we don't have more row, we don't have more column. This will be the last element. So it will be 1, 0 multiplied by 1, 3. So that will be 1 times 1 is 1. and this is 0 times 3 is 0, so it will be just 1. So we have then that AB, the product, is 4, this element, 14, and 1, 2, and to 1 will be negative 10, and to 2 is 1, and 3, 1 is 2, and finally M32 is 1. So this is the answer. This is AB. Let's solve another example. If H is this matrix, a 3 by 3 matrix, and D is this matrix, a 3 by 2 matrix. My question is, what will be HD? And there is another question. Is it DH possible? Okay, so first, let's answer the first question. Let's compute HD. They tell me that it's possible. Let me see. There are 3 columns in the first matrix and 3 rows in the second matrix. So the multiplication is possible, HD. So the entry located in the row I and column J of the matrix HD must be the product of the row I and of matrix A and the column J of the matrix B. So for sure it will be possible because we have here 3 columns in the first and 3 rows in the second. So HD will be first row, first column. Then will be first row, second column. And this will be possible, all these products, because the corresponding vectors will be always of the same size. Because they have 3 columns, each row vector will have 3 components. Because you have 3 rows in the second matrix, so each of the column vector will have 3 entries. So each product will be possible. You can see that this is well done. For example, here the last element will be the last row of the first matrix multiplied by the last column of the second matrix. And then do all this multiplication. Each of these multiplication will be a number. For example, here will be 2 times 2 is 4. 4 times 4 is 16, so it will be 4 plus 16, 20. Because this negative 1 times 0 is 0. Remember that you need to multiply and add together to make each of these multiplications. And again, we are going to notice that this will be very fast using a software. But obviously, let's practice how to do it by hand. Yeah? So that will be what you need to do. Multiply each row of the first matrix by each column of the second matrix. Okay, so this will be the answer. You should do it slowly if you are practicing. Now, what I'm going to see is to answer the second question. Is it DH possible? Let's analyze this. D is a 3 by 2 matrix. And H, if I want to make DH, the product DH, D will be the first and H will be the second matrix. So D is a 3 by 2 matrix and H is a 3 by 3 matrix. And I notice that here the number of columns of the first matrix and the number of rows of the second matrix are not equal. So they are not equal. For that reason, this product is not possible. So HD is this matrix, but DH is not possible. So this is completely different that we know about numbers, that the order of the factors doesn't change the product. Yeah? So the product is the same if we have numbers. But if we have matrices, sometimes we have a product in one order and we don't have a product in the other order. So matrix multiplication is not a commutative operation. Let's make another example. We have this matrix 2, 0, 1, 1, 0, 1 that is a 2 by 3 matrix. And we have this, a 3 by 2 matrix. The first matrix have 3 columns and the second matrix have 3 rows. I know that BC is possible for sure. So, and this is the question, compute BC. But is CB possible? But let's answer the first question, BC. That for sure is possible because you have 3 columns, the first one, 3 rows, the second one. For sure we can multiply 2, 0, 1 multiplied by 0 minus 2, 1. So let's open a bracket and put all the corresponding products in each of the entries. So for example, the first entry of this matrix will be 2, 0, 1, the first row, multiplied by the first column of the second matrix. Or the second element of the first row will be the first row of the first matrix multiplied by the second column of the second matrix. So it will be 2, 0, 1, 2, 1, 0. It will be good if you reviewed all these products are good. Okay, if you make this multiplication, for example, this is 2 times 0 is 0 plus 0 times minus 2 is 0. So I know that the first element here will be 1. Here for this one will be 2 by 2 is 4. The other is 0 plus times 1 is 0. 1 plus 0 is 0. So this number for sure will be 4. In this the second element in the first row of the matrix product. And it will be this is 0, this is 0, and this is 1. So this number will be 1 here when you multiply this. Or when you're multiplying this, the answer will be 2 for sure, because 1 by 2 is 2, 0 by 1 is 0, and 1 by 0 is 0. So this is the answer, 1, 4, 1, 2. This is BC. But what about CB? Now I'm going to consider that C is the first matrix, C is a 3 by 2 matrix, and the second matrix, B, is a 2 by 3 matrix. And I noticed that these two numbers are the same, so they are equal. So CB is also possible. Let's find it. So CB will be, now I need to get first the first matrix, CB, C, and B will be the second matrix, and now we have first row, first column, third row, second column, and first row, third column. So we'll notice that the matrix will be a 3 by 3 matrix, as in the previous one was a 2 by 2 matrix, because they have 2 rows and they have 2 columns, 2 by 2 matrix. So this one will be a 3 by 3 matrix. Anyway, will be different, the products. So the matrix result will have 0, 2 multiplied by 2, 1, the vector 0, 2 multiplied by 2, 1 in the first row, first column, and the first row, second column will be 0, 2, 0, 0, etc. So we multiply each of the row of the first matrix by each of the column of the second matrix, and the result will be like this. For example, in the last one, observe that will be 1, 0 multiplied by 1, 1 is this element here at the end. Or for example, the elements in the second row, second column will be the second row of the first matrix, second column of the second matrix. Or for example, the element in the third row, first column. This element here will be the third row of the first matrix multiplied by the first column of the second matrix. Okay, do each of these multiplication. For example, in the first one will be 0 times 2 plus 2 multiplied by 1. And this is 2, because the 0 times 2 is 0. Or the second one will be completely 0, because the two elements are 0 here. You can check all this multiplication, and the answer is this. CB was possible, but notice that it's completely different to BC. So if matrix multiplication is possible, the product BC is not necessarily equal to CB. Definitely we have to check that BC and CB in this case are different. So matrix multiplication is not commutative. Let's finish with the last operation that we're going to speak about, matrix transpose. This is a very easy operation. Let A be a matrix of psi n by n with elements I, j. The transpose of A symbolize AT. I'm going to symbolize it in this way. There are some textbooks that symbolize it in a different way. It's a matrix of psi n by m. So if the initial matrix is m by n, the result of the transpose will be n by m. So the number of rows of the original matrix will be the number of columns of the result, and the number of columns will be the number of rows in the result. And the entry will be AJI. So if one element is in the row I and column J of matrix A, in the transpose of A, this element will be in row J and column I. So we are changing rows and columns. So the transpose of a matrix is merely a flipping version of A. The rows and columns of the original matrix become respectively the columns and rows of its transpose. For example, if we have this matrix that have 3 rows and 2 columns. The transpose of A will have 2 rows and 3 columns. So then AT will be the matrix that have the first column, the first row of the matrix A. So it will be 2, 4 here. And the second column will be the second row of matrix A. So it will be -5, 2. And the last column will be the last row of A, 1, 0. So it will be here 1, 0. And this will be the transpose of 8. If B is this, and assume that we want to compute B transpose. B transpose, of course, will be flipping this, the matrix that I have at the first column 1, 4, -1, 0. And the second column will be 2, -2, 1, 2. So 2, -2, 1, and 2. Close the bracket, and this will be the matrix BT. So the multiplication of these two matrices will be this, BBT. It will be 1, 4, -1, 0, and 2, -2, 1, 2. Multiplied by X transpose. So we have just to multiply the first row, first column of the first matrix. So 1 times 4, 1 plus 4 times 4 plus -1 times -1 plus 0 times 0. Each number multiplied by itself. Yeah? So we have here 1 times 1, 4 times 1, 4 times 4, -1 times 1, and 0 times 0. In the first row, second column of this matrix result, it will be 1 times 2, 4 times -2, -1 times 1, and 0 times 2. I have typed it here. This element will be second row, first column of the second matrix will be 2 times 1 plus -2 times 4 plus 1 times -1 plus 2 times 0. And finally, second row, second column, 2 times 2, -2 times -2. Again, each number by itself. Do you notice? Do you notice that multiplication in the first row, second column, is the same of the multiplication in the second row, first column? Because are the same numbers. So when you multiply this by this, second row here multiply the first column in the second, is the same of multiplying the first row of the first matrix times the second column of the second matrix, obviously, because this is a flipping of this. So let's cross the bracket and just make this operation. This is 1 plus 16, 17 plus 1, 18. So 18 will be here. Here will be 2 minus A. It will be -6, -1, -7, plus 0, -7. You can continue in this way. Yeah? So it will be 18, -7. This will be -7 also. And here will be 4 plus 4, 8, 9, and 4, 13. So we have 13 and close the bracket. Do you notice that this operation is always the same of this? This is a property when you multiply a matrix by its transpose. The answer will be a matrix in which the elements below the main diagonal will be the same elements above the main diagonal. This type of matrix are called symmetric matrices. So a symmetric matrix is a square matrix that is equal to its transpose. A with these elements is a symmetric matrix if it's a square matrix and the element that is in the row I and column J is the same that the element that is in the row J and column I. For example, this matrix, we notice in this matrix that A21 is this 4, A12 is this 4, or A31 is this -1, A13 is -1, A41 is this 5, A is in the 4th row, first column is the same element that is in this first row, 4 columns, is 5, or A42, A42 is in the 4th row, second column. It will be the same that the element that is in the second row, first column, 11, etc. So this is a symmetric matrix. This is another example of a symmetric matrix. You can check that each element, of course, if you compute the transpose, the answer will be the same. And this is another example of a symmetric matrix. Or this one is an example of symmetric matrix. A 2 by 2 matrix, the only that need to be symmetric is that the elements A21 will be equal to the element A12. There will be some situations in which several operations are involved. In this case, follow the rules of operations that we followed in the usual mathematics. For example, if we have this matrix A equal this 3 by 2 matrix and B is this 2 by 2 matrix, and we want to compute this 3/8 transpose A multiplied by A minus 4B squared, what to do? Solve first the transpose, it looks like an exponent, and then multiplications later. For example, for this term, first the multiplication, this B squared will be B by B, B times B, and multiply by 4 first before making these subtractions. So let's get first the A transpose. The transpose of A will be easy. You just flip in the matrix and you get this matrix. Now it's a 2 by 3 matrix. And then you can make now the multiplication. A transpose times 8. So then A transpose times 8 will be first. The transpose need to be first. So remember that the multiplication is no commutative operation. So you will need to be careful with the order. A transpose will be first, then A the second, and multiply the row of the first matrix multiplied by the columns of the second matrix. The result will be a matrix of 2 rows, 2 columns. So the number of rows of the first one, the number of columns of the second one. A 2 by 2 matrix. You can check that this is the result. 9, 4, 4, 13. Now that you have this, you can multiply by 3. So 3/8 will be 3 times this. 3 times 9, 4, 4, 13. 3 times 9 is 27. This will be 12. 3 times 4 is 12. 3 times 4 is 12. And 3 times 13 is 39. Remember, you will need to multiply each of the elements of the matrix by these 3. So you get this answer. So you have the first term. For the second term, again, first the power, and the power actually B, we don't know the power of a matrix, but we know that B squared is the same of B times B. So you just need to multiply these two matrices, each row times each column. You can verify that the answer is this, 6, 3, 2, 7. So when you multiply, for example, the first row times the first column will be 0 times 0 plus 3 times 2. That is 6. So it will be 0 plus 6. It will be this 6. Or for example, for the second number here, in the first row, second column of the result will be 0 times 3 is 0 plus 3 times 1 is 3. So this will be the number 3 that appears here. You can verify all the numbers that this is the answer. And we will be making later this using a computer, don't worry. So we are solving at that moment by hand. Okay, and then we need to multiply by 4. So it will be, then 4b squared will be 4 times this matrix. So this will be 4 times this 6, that is this 24. 4 times this 3, that is this 12. 4 times 2, that is this a, and 4 times 7 is 28. So now that we have the two terms in this expression, 380a minus 4b squared will be this matrix minus this matrix. So it will be this matrix, that is 3a transpose a, minus this matrix, that is 4b squared. So making this subtraction will be subtracting element by element. 27 minus 24 will be 3. This number here will be 12 minus 12 will be 0. 12 minus a, 4. And finally 13a minus 20a, that will be 11. So this will be the answer, 30411. So this is in case that you need to do an operation by hand. Of course, because this involves a lot of operation, it will be better using a software. To finish this video, I will be speaking about some properties of matrix operations. For the following that I'm going to say, A, B, and C will be matrices of the same size, n by n matrices. And 0 will be a 0 matrix of the same size. When you see this O here, it will be symbolizing a 0 matrix of the same size of A, B, and C. Then if this is true, then we have the following. Commutative property of addition. So the addition will be commutative. So adding A plus B will be the same of B plus A. If you have two matrices, this will be the same. So they produce the same matrix. The associative property also holds in matrices for the addition. And for the multiplication, we'll see that also. So A plus B plus C, if you need to add three matrices, you can add first the two last, and then when you get this answer, add the other. Or you can add the two first and add the third at the end. Anyway, in whatever order you make the operations, the answer will be the same. We say then that the addition satisfies the associative property. We have also the identity property of matrices. So if you add the matrix A plus the matrix 0, the answer is the same of adding the matrix 0 plus the matrix A, obviously, because the addition is commutative, but the answer will be the matrix A. And finally, there is an inverse property of addition of matrices. So you can find a matrix that adding to A, the answer will be 0. And it will be easy finding this matrix. You will notice that it will be just changing the sign of each of the elements of the original matrix. If we have A, B, and C matrices in such a way that the operations that I'm going to speak about are possible, so we know when they are possible, the additions mean that they need to have the same size, and the multiplication, you know that the number of columns of the first matrix need to be the number of columns of the second matrix. And let I represent the identity matrix of appropriate size. So in such a way that you can make the multiplications. And this will be the identity that we will satisfy the identity property for the multiplications. This matrix, remember that I is a diagonal matrix when all the entries are 1. We know that there is an I for each side. This will be the i's, the appropriate size, depending on the matrix we have. Okay, then we have the following. Associative property of multiplication of matrices holds, okay? So again, if the operations are possible, then you can multiply BC, and then after you find this, multiply A times BC. Obviously, putting A at the beginning, you know that the order is important. So put A first, but multiply first BC. And then when you finish this multiplication, multiply by A. It will be the same answer if you multiply AB, and when you solve this, multiply the answer by C. If you do that, in these two different orders of association, no order of matrices, the A cannot be in the second position or the third position, no. A at the first, B second, and C in the third position. If you don't change the position, but you change the order of the operations, it will be possible. So associative property, as in the addition, it holds also in multiplication of matrices. Another property that holds is the identity properties. So if you multiply a matrix by the identity, if this multiplication is possible, so if you multiply A by the identity, that the identity in which this multiplication is possible, then the answer will be A. And if you multiply the identity by A by the identity in which this multiplication is possible, the answer will be A. So there is no change in multiplying by the identity if the multiplication is possible. And finally, the distributive property of multiplication means that if you can multiply A by a sum of matrices, if you need to do that, obviously you can add together the two matrices and then multiply by A. I think it will be the easier way to solve it, solving the problem in this way, because addition is very easy and there will be only one multiplication. But this will be the same as if you have the first matrix multiplied by B and again the first matrix multiplied by C and add later. So it will be adding first and then make just one multiplication. It will be the same that multiplying each of the metrics by a, with a at the beginning, with a always the first matrix. Obviously, if a is at the other side, if the other product is possible, the same. This BC multiplied by a will be equal BA plus CA. So you can just add first and then multiply, or multiply the two matrices by 8 and then make the addition. For me, it will be easier if you have this problem. It will be easier if you solve it in this way. You will need to make only one multiplication. But what I'm telling you, that is the same. The answer will be the same. Okay, the only thing that is missing for this week will be how to make the operations using software, because we know that there is a lot of work involved here. It will be a good idea to use software to work in matrix operations. So we are going to, I'm going to show that in another video. Just remember, matrix multiplication is not commutative. AB is not necessarily equal to BA. There will be a few situations when AB is equal to BA, but in general, AB is not necessarily equal to BA. We have already spoke about this.